All right, I'll get started. Welcome, everybody. My name's Trey Grainger, and today we're going to talk about integrating real-time user behavioral embeddings into OpenSearch. Decided to have some fun with this one. I'm the author of AI-Powered Search, the lead author, along with Doug Turnbull and Max Irwin. We'll talk about what we're doing in that space a little bit. Background about me, I'm the founder of Searchkernel, an AI-powered search consulting company. I'm a technical advisor to Open Source Connections. Been teaching as an adjunct professor from university. Previously served as the CTO of a decentralized web search engine, the head of engineering, and the chief algorithms officer at LucidWorks, a search company. And prior to that, worked at Career Builder, running their search teams. Wrote a few books, wrote Solar in Action about a decade ago. AI-Powered Search is the new book that just came out this year. If you're interested, it's 45% off if you use that code while you're here at the conference. If you don't have a copy, we cover pretty much anything you would expect in an overview of different AI-powered search techniques, approaches, everything from signals-based, user behavioral-based stuff like we'll talk about today, using that to do recommendations, personalized search, build click models for automated learning to rank, and as well as what you would expect in terms of dense vector, sparse vector, quantization, and lots of different approaches to query intent understanding. In addition to the book, one of my co-authors, Doug Turnbull, and I are actually doing a live course. It's going to be a cohort-based course we're going to be teaching in November. If you want to dive a bit deeper, then we get into the book and cover some more topics, and you'd like to learn in a cohort-based class with lots of peers from across the industry and learn from Doug and I. We'll have about 3 to 6 hours of material every week for about a month. Live sessions will all be recorded, so you've got the material if you are, you'll have the material if you can't make a session. You can always watch the videos later. But we just launched this last week, and we're gearing up for a really fun November. So if you would like to learn directly with us, there's currently a 30% off code up there, OpenSearchCon, good just for this week. So if you want to check it out, see if it's something you'd be interested in, it'll be a lot of fun learning with us and some guest speakers. It's online on Maven, so everything is through Zoom, and we'll have the ability for you to interact with us. We also have office hours, so if you want some sort of light consulting during that time, feel free to pick our brains with whatever. So definitely check that out. I see a few people getting the QR code there, so I'll show it at the end as well. But that's my quick plug for everything related to AI-powered search, other than we also have a community associated with the book. So if you get the book or attend the training, we've got an online community. Last check, we had like about 850 people who've joined. It's not super active right now, but there's a lot of people there, and I've got some really big plans for it. So definitely, if you would like to engage and interact with us, check it out. And I would love to see you on there and talk about any AI-powered search-related topics you're interested in. So for today, we'll talk about user behavioral embeddings. Our agenda, at the very beginning, we're just going to do a light refresher on embeddings and talk about latent features and sort of what embeddings represent. We're going to talk a little bit about OpenSearch's user behavior insights and how you can log user interactions, clicks, add to carts, purchases, those kinds of things very easily in OpenSearch. And then we're going to talk about how we leverage those how we leverage the click searches, et cetera, in order to derive some embeddings based upon those behaviors, as well as use it to actually generate personalized search results. So we'll talk about the personalization spectrum between search and recommendations, leveraging user signals to implement collaborative filtering and personalization from those latent features, using embedding vectors to generate personalization profiles, mixing user signals and content-based attributes to generate multimodal personalization, clustering products by embeddings to create personalization guardrails, and finally, some of the pitfalls of personalized search and why you may or may not want to use some of these techniques. So very quickly, everybody knows this, but just to level set, we'll talk about embeddings. Everybody knows what an embedding is. You can generate embeddings from any parts of text, words, phrases, sentences, paragraphs, documents. You essentially take the embeddings for those different subpieces and kind of pull them together to create a larger embedding of the document typically. An embedding functionally is really just a set of coordinates in vector space into which we can map a concept. So most of the vector spaces we work with embeddings are sort of semantic spaces. So we're looking at things that are similar in meaning or sort of clustering together within those spaces. But at a very basic level, whether you're dealing with dense embeddings, which might have less than 1,000 to a couple of thousand dimensions that are tightly packed, or whether you have sparse spaces where you could imagine, for example, if you've got an OpenSearch index, you could think of every single word in that index as a dimension. Say there's 1 million words in your index, then you've got a vector space with 1 million dimensions, and you could represent the items in that space just based upon a 0 or a 1, one-hot encoding here, representing whether that particular lexical term exists or not. So for example, latte, imagine there's 1 million different columns here, 1 million dimensions. And latte is not in my index. We'll, hold on one second. Yeah, let me not do latte. Let me do apple, cheese pizza. So in this case, cheese pizza as a phrase is represented by the vector, cheese is there and pizza is there. Donut is represented by a vector with all zeros, and just the word donut is there. So this is this is a sparse vector because most of the dimensions are not filled in, even though there's a massive number of dimensions here. And so most of the embeddings that we work with, if you get them from like a transformer, are going to be dense embeddings, which have a much lower number of dimensions, but those dimensions are sort of collectively representing a lot more. And you can think of this as basically just a lower dimensional space. So if you took all of those dimensions we just looked at, run them through the neural nets, and you generate more conceptual embeddings. What I have here is not what a transformer does. This is just a conceptual model. So what I've essentially done here, though, is I've taken all those words and I've reduced them down to a finite number of dimensions, in this case 8. So I've got 8 dimensions that are very explicit and partitioned off, right? So food is one of those dimensions, drink is one of those dimensions, dairy, bread, caffeine, et cetera. So if I look at something like apple juice, it's very much not food, very much a drink, not dairy, not bread, not caffeine, very high on sweet, very high on calories, and kind of in between but tending towards unhealthy, right? If I look at something else like green tea, it's very much not food, very much a drink, no dairy, no bread, a little bit of caffeine, little bit sweet, but not really, depends on what you put in, I guess, and a little bit of calories, and then healthy, very healthy, and these really just depend on where you get it from. But if you map all of these items into these 8 dimensions and give them scores, I've got an 8-dimensional embedding here that it's not what you would get from a transformer, but it represents the concepts of each of these items. And so then just how we do vector search typically, right? You take either documents or terms or what have you, you represent them as vectors, and then you do some similarity metric. Let's just take a cosine for now. And then whether, again, these are representing documents, terms, or what have you, we can say that if I want to score the results for cheese pizza, I just take that vector for cheese pizza, do a similarity metric, cosine in this case, and then I can rank all of the items based upon how similar they are to cheese pizza. So cheese breadstick shows up at the top, cinnamon breadsticks next, donut next, because these are all, this is the breadiest, cheesiest, foodiest thing, right? And then down here, this is the thing that's sort of on the opposite end of the spectrum from those dimensions. Same thing with green tea. You guys hopefully understand this, if you've been working with vector search for a lot. This is no surprise. And this is just like a very simple model of using a vector. We'll talk about transformers and latent spaces in a second. But when we take embeddings, and we sort of, if we take a bunch of images, generate image embeddings for those, and we map them out here, right? So if I look at this cluster over here, if I were to look for Darth Vader, right down here is sort of a cluster of things related to Darth Vader. And if I go to look at the images there, these are some images that are in that sort of cluster of items in that area of vector space. If I instead search for puppy, then you can see there's sort of up at the top left, there's a giant cluster related to puppy, and there's other things spread around, but in general, puppy's gonna be right there. And if I select a few of the items that are in that area of vector space, I get some nice, cute puppies over here. So the question, though, is given that this is representing sort of concepts across vector space, what happens if I, across all those dimensions, go to the midpoint between puppy and Darth Vader? What am I going to find there? And again, if puppiness is this way and Darth Vaderness is this way, and I'm looking right at the middle between those two things, then I'm going to find something like this, right? A Darth Vader cute little puppy thing. That's the interesting notion in these kind of vector spaces is you can do vector math. You guys all know from the old Word2Vec paper, like the woman, what is it, king minus man plus woman is queen, I think. And so it's the same concept. I'm just moving around and using the math in vector space. And so with LLMs and other foundation models, that simplistic example I gave you of the food items where I had 8 discrete dimensions, that's not really what we do. We have massive numbers of dimensions, and those dimensions all sort of collectively represent what we're looking for. And so we call them latent features because there's these sort of these hidden features that are being uncovered by these models. And so I'm going to today talk a little bit about taking user behaviors and generating user behavioral-based embeddings, and also taking regular embeddings and using user behaviors to generate embeddings we can use for personalization. So this is a general mental model that I like to use for describing what we do when we're trying to solve search relevance problems. It's the dimensions of user intent. There's 3 kind of key categories here. So when somebody types in a query and they're looking for they type in a query, there's content itself that you're searching, there's user behavior and sort of like understanding the user and what they're looking for, and then there's this notion of domain understanding. And so, if you're in e-commerce focused on home improvement, then there's a whole bunch of things related to that domain. And if you think of these independently, then if I'm only looking at the content that I actually have in the engine, like the text in particular, then this is basically keyword search. I'm just doing kind of lexical query. Maybe I'm doing some vector-based stuff here, but I'm just looking at the content. If I'm only looking at the domain understanding, it's not really tied to my content, not really tied to my user, then that's a knowledge graph. It's a representation of the meaning within my domain, but not directly tied to either of these. And if I only look at user understanding, what are my users doing? What are they searching for? What are they clicking on? What are they interacting with? This is independent of my content, the keywords and other material in my content per se, and independent of the knowledge graph. This is where we typically have things like collaborative recommendations, where just purely based upon the users and their behaviors and interactions, I can understand something about them without necessarily tying it to the terms in my search engine and the knowledge graph. But the interesting thing is when we look at the intersections of these. And so if we look at the intersection between my content understanding, my domain understanding, that's where we have things like semantic search. And today what we're going to talk about is this area here where I'm looking at the intersection between the content I have and what my users are doing and how they're interacting with that content. And that allows me to generate personalized search. Throughout the AI-powered search book, there is probably about 1/3 of the book focuses on these user signals, behavioral-based approaches, something we call reflected intelligence. And it's very basic. It's similar to reinforcement learning, where you're basically, in this case, every time a user runs a search, they see some results. We log those results. They take some action. Maybe they click, maybe they add to cart, maybe they purchase. We log that. And then we use those searches and those actions to build a model that can improve the next search. So at a very high level, there's a whole bunch of reflected intelligence models in the book, but at a very high level, they all sort of work this way. So somebody searches for iPad. We log who searched for it, what their query was, and what results they saw, and the ones they didn't see. We then log whenever they take an action, clicks, purchases, et cetera. We then we take those signals and we process them to generate some kind of a learned relevance model, and then we feed that learned relevance model back into the system so that future searches can leverage that model to improve. So some examples of reflected intelligence models, I'm not going to go through them today, but there's whole chapters in the book on these, are things like signals boosting, where you take the most popular items that people are searching for or are clicking on for any particular query, and you boost those up. This tends to work really well for your head queries. There's the ability to generate click models to do learning to rank. It's another way to leverage reflected intelligence. And what we're going to talk about today is collaborative filtering and matrix factorization. So in OpenSearch, I've mentioned user behavior insights. There is an ability to take in signals from users, queries, clicks, those kinds of things. I'll actually flip ahead to what this looks like. And you can enable this in OpenSearch. And what it allows you to do is, as a query comes in, you can take my query, say someone searched for iPad, and you can then attach UBI information associated with it, the query ID, client ID, objects that are being interacted with. You can log searches, you can log behaviors, if somebody adds to cart purchases, those kinds of things, you can log all of those. In the AI-powered search book, we also have a format for those types of things to be logged. So we've got a whole data set, this in the e-commerce domain, that allows us to take queries, signals, dates, times, those kinds of things. And we have a notebook, which I'll actually flip over to. I'll show you what it looks like here. We have a notebook that will actually take the data set in AI-powered search and send it into OpenSearch, either directly as a bunch of searches and follow-on signals, synthesizing real user behavior, or we've got a Spark job that'll just load them directly in so that you can use what's in your OpenSearch cluster with all the algorithms in the book. I'm going to actually just flip over screens for 1 second, show you what those notebooks look like. By the way, everything in the book is open source, so sorry. Okay, so this is our notebook for, maybe a little bit bigger. So this is our notebook for UBI. So we have the ability we've got a bunch of product data and we've got a bunch of signal data. We can, let me scroll down to the interesting part. So this is all like loading with Spark, just directly in for batch processing, but we also have this example where you can live log queries and events. So if this is my product collection, I've got, you come here, product, UBI, query. So yeah, so this is an example of me sending in a search request for a query. Let's see if I can, so whatever my query is, I'm looping through all my queries in my data set. I'm sending in the query on the fields I'm searching on, and then I'm passing in this UBI extension data with the actual query being passed in, and then the same thing for my other signals. UBI event, so I've got UBI events, UBI queries. I can pass those all in, and once I've indexed them, if I go to my UBI dashboard, then you can see this is the native OpenSearch format for representing all of the signals. So I've got a bunch of clicks, I've got a bunch of purchases, and I've got a bunch of add to carts. You can kind of see what the queries are that are coming in. Once I've done that, and by the way, if you have your own OpenSearch cluster now and you're using UBI, then all of these algorithms I'm about to show you, you can just point them at your collections in OpenSearch, and these algorithms will just run. So you can play around with personalization or collaborative filtering, what have you. But I just want to give you the general setup there for the starting point of using this with OpenSearch. Let me go back to the slide now. And so once I've got the data there, what are the common things that you would do with user behavioral signals? One of the most common things is recommendations. I've got a bunch of user behavior. Let me use that to generate recommendations for them. And so traditional recommendations, you'll see over here on the far right, this is like collaborative filtering. And traditional keyword search, you'll see here on the far left. I refer to this as the personalization spectrum. And if you think of recommendations as a process of taking in user context, passing it to an engine to sort of match and rank, and then to return recommendations as results. It's really not fundamentally different than what we do with traditional keyword search. With traditional keyword search, you take in a query as context, use that context to match and then rank, and then you return some results. So whether the context being passed in is specific keyword queries the user typed, or whether the context being passed in is the behaviors and interactions from the user previously, both of these are just taking that context, matching and ranking. So if you think of the search engine, if you think of OpenSearch as just a matching and ranking engine, you can actually power recommendations or search based upon the underlying indexes. And so this sort of area in between where I've got personalized search, which is mostly user-driven, but the ranking is being sort of tweaked and adjusted based upon what we know about the user. Or if you think of user-guided recommendations, where we have recommendations, and after they've been generated or while they're being generated, we give the user the ability to adjust the features that go in. Hey, I don't want to use these particular items as part of my recommendations, or I want to filter out certain groups, or what have you. And so but you can sort of do anything along the spectrum, depending upon the combination of user interaction data on the recommendation side, user understanding side, and whatever searches are being typed in on the traditional keyword search side. And so if we think of recommendations, we also know that there's lots of ways to do recommendations, right? There's content-based recommendations, where I have somebody here, they searched for detergent previously, maybe they searched for some other things, and I'm then relating laundry across different items, because maybe they searched for laundry previously, so I'm finding other items with laundry. Maybe they searched for clothes, I'm finding other items with clothes. And so there's the ability to use the content itself just to generate recommendations. And of course, we can use the user behavior. This is known as collaborative filtering. In this case, I maybe have somebody who search for fertilizer. Other people previously who have looked for fertilizer and clicked on it or added it to their cart also looked for soil and mulch. Similarly, people who search for hammer also tend to search for screwdriver and nails. And so we learn that those things are related based upon how people interact with them. And of course, you can do sort of hybrid recommendations where you use both content features and behavioral features, and generate even better recommendations by sort of getting rid of the cold start problem you have with collaborative recommendations, and overcoming some of the lack of sort of user behavioral understanding you have in the content. And so that's all kind of background for where we're going. And what I want to talk about next is leveraging some of these concepts to generate latent behavioral embeddings that we can use for personalization. So very quickly, collaborative filtering is the process of typically leveraging something like matrix factorization to take user item interactions, to decompose those into typically two matrices, one a sort of user features matrix and one an item features matrix. And then typically once you've generated that, you try to approximate that original matrix by generating a new matrix that has all of the sort of missing data filtered. And I'll show you an example of that in a second. But this is just a basic collaborative filtering algorithm here called alternating least squares. This is some example Spark code. It's in the notebooks in the AI-powered search code repository. But all I'm doing here is I'm taking a bunch of these user signals, the clicks, purchases, et cetera, that are stored in user behavior insights, and I am now generating recommendations on the other end. And so if I were to take a particular user who previously searched, for example, for Apple and MacBook, these are their product interactions. They clicked on an iPad, on an iPad 2, they purchased an iPad 2, et cetera. I can then use those behaviors, go to this collaborative filtering model that's been built to look at the learned values for the user item matrix, so the user matrix, and then try to find recommendations for them. These are the kinds of recommendations that I get out on the other side. This is functionally being implemented as running a search, boosting on the items that are found to be relevant for that user as recommendations, but fundamentally I'm using the search engine to serve my recommendations. If I were to run a search without those boosts, for example for tablet, then I would get something like this. These are really bad results, obviously, but they match the keyword tablet quite well. So, tablet sleeve, media tablet, stone tablet, et cetera. I think everybody in here would agree that these are really awful actual search results. But what I can do is by combining these weights that I learned from collaborative filtering for recommendations and the keyword that the person is typing for lexical search in this case, I can generate keyword search results where the results are boosted based upon the collaborative filtering results. So in this case, the user searched for tablet, and you'll notice at the bottom, I still see those really bad results that are just my pure lexical search. But out of all the results that match tablet, I've now boosted these results to the top because they're more relevant for that user. So this is an example of personalized search, where I'm both taking the context of what the user typed in for traditional keyword search, and I'm also taking in the context of their behaviors and what I've learned about them, a la recommendations, and combining them in this query. It's still filtered on what they searched for, but we're boosting things that they're probably more likely to be interested in. And so, interestingly, if we think of a traditional LLM, like you think of calling like OpenAI and generated embeddings, leveraging their models, the embeddings are typically dense embeddings that have latent features. So as a mental model here, I've got a bunch of floats here. So these are my sort of latent features down here. Say I have 768 dimensions. This particular dimension here, if I look at these things here, I can see that this roughly correlates with size. It might be some combination of fields, but what I can say is that the bigger thing here, 8.2, 7.7, those are bigger and they tend to have a larger number. This one's the smallest thing, it tends to have the smallest number. If I look at this particular dimension, it roughly corresponds with color, where black things tend to have a higher value, and things on the sort of white spectrum, the white side of the color spectrum, tend to have this value, et cetera. This roughly corresponds with, is this computer-like? This dimension roughly corresponds with price. And in practice, because these are latent features, they're spread across lots of different dimensions. It's not as clean-cut as this, but conceptually, there's these fuzzy mappings of concepts across the data. So to do this as a practical example, thinking of collaborative filtering, which we just looked at with that alternating least squares algorithm, collaborative filtering also relies on latent features. So for example, let's say I've got 5 users here. The first user likes these first 3 items, Avengers Endgame, Black Panther, and Black Widow. The second user likes Black Panther, Black Widow, Captain Marvel. The third user, Black Widow, Dark Knight, and Batman. I'll just kind of show these as we go. First user, second user, the third user likes these, the fourth user likes these, and the fifth user likes these. So we can use a collaborative filtering algorithm to figure out, based upon what a user has interacted with, what other things are they most likely to like, based upon what other users have done. But the reality is, if you and I look at this data, our brains can pick out the latent features that are sort of embedded in these interactions. For example, we can see that user 1, user 2, and user 3, all of these tended to like movies about superheroes. Most of them were made by Marvel Studios, though some were made by Warner Brothers or DC Comics. They're all action movies, and they're all not really suitable for small children. If I look at user 4 and user 5, starting with kind of The Little Mermaid and over, all of these are animated movies. They're all suitable for small children, and they're all made by Disney and Pixar. These are latent features associated with these items that are being surfaced up through the underlying embeddings that are happening internally whenever collaborative filtering is being done through matrix factorization. So let's talk about what that matrix factorization looks like. So to do this alternating least squares algorithm, our starting point is taking a bunch of users and a bunch of items. So in this case, I've got some movies, and I've got some users. These are the values I actually have filled in. And what I'm trying to do with the matrix factorization is to take this original sort of somewhat sparsely filled matrix, and then to decompose it or factor it out into 2 different matrices. One is this user feature matrix, where I've got the users here, and then 3 different latent features that are being learned. Again, the latent features are representing the sort of underlying concepts of why these things are related. So if I take these, then I can figure out sort of these 3 latent features, and then up here, I can take each of the movies and also generate latent features for them. And so in this case, I'm only generating a 3-dimensional embedding. But what you can do is think of all of these latent features as just an embedding. And so to do collaborative filtering, I take these 2 matrices here, and I can multiply them together to generate this other matrix, which roughly approximates that original matrix. Once I've done that, now I can generate recommendations for any user by figuring out, for that user, let me get their, so if I want to figure out, for example, how much this person is going to like The Notebook, or if I'm trying to figure out how much this person is going to like Avengers Endgame, I can do multiplication of these matrices, and I can generate a score of 9.32 for this user and a score of 9.98 for this user, saying that this user is very likely to like Avengers Endgame, and this user is very likely to like the movie The Notebook. I may or may not have modeled those two users after my wife and myself, with me being Avengers Endgame and her being The Notebook. I'm not saying I did or didn't, but this would roughly correspond to if I did. And you can see that we can generate recommendations for any of these items, and this is how collaborative filtering works. But the kind of key point here is that we can also just use these latent features directly as a behavioral embeddings. So if I just think of this user and what they're interested in is being represented by this three-dimensional embedding, this user is represented by this three-dimensional embedding, and these items also have these embeddings. What I've essentially done is learned an embedding model from my user behavior that I can then use for relevance. So that's one approach where we can sort of get additional dimensions to put in the search engine. Another approach, which I'll go through kind of quickly here, is generating LLM-based embeddings for personalization. So in this case, what I'm trying to do is say, based upon my users and what they've interacted with, let me take the embeddings for those items and sort of describe the user based upon the sort of collection of documents they're interested in. If I pool those embeddings or sort of average those embeddings together, I can get a sense of what the user likes. There's some problems with doing this. So the naive approach, which I just described, would be just to say for every user, look at all the documents that they've interacted with and average the embeddings of those. And then that would generate a personalization vector for that user based upon the collection of all of those. The problem with that is that based upon the context of what the user was searching for, it may not be suitable to use all of the items they've ever interacted with. And so here's an example where I've got a user who previously searched for a Hello Kitty plush toy. And when I say search, they searched, clicked. There's just some signals saying this user liked the Hello Kitty plush toy. They also searched for a GE electric razor. They previously searched for GE bright white light bulbs, and they previously searched for Samsung stainless steel refrigerator. And now they're coming and they're running a search for microwave. So the question is, does it make sense to take all of those items that they've interacted with in the past and average them together and say this is a vector that represents the user? And I would posit in general, no, it doesn't. So if I use all of these things and run a search for microwave and use a vector representing all of these, then I might get results that look like this. A black GE microwave, because they previously searched for something from GE, a razor, and it was black. I see a Hello Kitty microwave. Why? Because they searched for a Hello Kitty plush toy. The results, if all of the searches they ever ran should be considered for this, these would be good results. But I would argue if they've previously searched for a stainless steel refrigerator and now they're searching for a microwave, most likely they would prefer to see a Samsung stainless steel microwave, which you see on the right. And so the ones on the left are pretty irrelevant based upon because they're using all the past behavior, and the ones on the right are only using the vectors from the items that are actually associated with the search being run now. So a better approach to generating user-based embeddings is to find the relevant query context and then generate user embeddings dynamically based upon that context. And so I'm not going to go through the code, it's in the book, but you essentially do this by first clustering all of the products in your catalog. This is an e-commerce example. And so then once we've clustered them, you can sort of see, here's my vector space mapped into 2 dimensions, and I can see things like, kitchen appliances are sort of at the top left, things like batteries, laptop are at the right. I can see over here that, things that are audio-based, CDs, music, those kinds of things are up here on the top right. At the bottom right, I've got things that are more visual. So you can kind of see roughly the kind of meaning of the vector space being mapped out here. But what I can then do is I can say for any query coming in, like microwave, before I go find a personalization vector associated with that and just use all of the items, what I can do is I can take microwave, I can try a couple different approaches. I could use k-means to find a predicted cluster. I could use cosine to find the most recent cluster. But what I prefer to do is to get sort of the top in, so the k nearest, in this case 5, clusters associated with the query that came in. So they search for microwave, and what I'm doing is I'm saying, hey, these 5 clusters, microwave stainless steel oven, stainless steel black range cooking, KitchenAid black white stand mixer. So these are just some examples of things in these clusters. I'm going to use those to apply a filter around those vectors that I can then use to only select sort of vectors associated with both the user and this query that came in, so that I can then personalize the query. So there's a couple of different approaches for how we can take these sort of embedding-based, so we can leverage the embeddings here. One's to perform a weighted average between the query vector, so the embedding for microwave, and the vectors of the user's previous interactions with the predicted clusters. Another is to perform a standard search, but then to boost the results based on the average of the embeddings from users' previous interactions with within the predicted clusters. We could alternatively say, do either one of those, but then only personalize a few items in the search results instead of all the results. So in this case, personalization doesn't just take over all the results. We maybe only personalize a couple of positions. And then this last one is to perform a standard search, keyword or vector search, but then re-rank the results based on the weighted average between the query vector and the vectors for the user's previous interactions within the predicted cluster. So that's my preferred way to do this. This is largely reusable across different search engines and generalizable. And so we'll kind of show an example of that. So again, not going to go into the code, but what I'm doing right here is generating a personalization vector for the user's query. So in this case, this user, these particular items were their interest. So what I'm going to do is I'm going to find a personalization vector. So these are products that they interacted with that are in those clusters associated with microwave. I'm going to then pull those vectors to generate a personalization vector, and then I'm going to find the products filtered to that. And then finally, the cluster sort of acts as guardrails around the vectors I'm using. And then I can generate my final filtered personalization vector with cluster guardrails. There's the code for it, but then you end up with what we saw earlier, which is if I just run a standard keyword search for microwave, then I end up with basic microwave results. If I use all of the user's behavior to personalize, I end up with this mixed bag of results. And then if I contextually personalize, meaning I find the clusters associated with the current query, in real time grab the user's previous interactions that fall within those clusters and only use those embeddings to personalize, now I can personalize specifically for this user so that when they search for microwave, I'm finding explicitly Samsung stainless steel microwaves at the top of the results, because those are associated with the previous interactions that are related to this category of kitchen appliances. So that's sort of a way to do this. Also, I should mention that it's possible. We've talked about taking both user behavioral embeddings, where I've learned them directly from matrix factorization on the user signals. I can use these as embeddings. I can combine them with the content-based embeddings or embeddings from any vector space. So I could, for example, take text embeddings. Let's see where my cursor is. I could take text embeddings over here to generate a vector. I could take image embeddings to generate a vector. I could take these collaborative filtering-based user behavioral embeddings and generate a vector. And then there's various techniques, whether it's concatenation, dimensionality reduction, or stacking that you can use to sort of combine those vector spaces. And then do just some really cool stuff. So most people don't leverage the user behavioral embeddings in their production systems to do personalization like this, mostly because it's really easy to do. It's really easy to generate embeddings from text and images because we have so many libraries and LLMs that do that, but it takes a lot of effort to collect all the user behavior and then use that to generate behavioral embeddings. The nice thing with OpenSearch, with the UBI plugin, is you can actually more easily store that data and then plug it into algorithms like this, like we have in the book. So there's lots of other ways that you can do search and queries. We kind of taught through them throughout the book, lots of different query modalities. There's also a lot of other reflected intelligence approaches in terms of, I mentioned earlier, like signals, collaborative filtering, learning to rank, and different ways to leverage the data you might store in user behavior insights. But that's the scope of what we can talk about today and the time we have. So I wanted to share that with you. Hopefully that's interesting. Be happy to chat with you afterwards. Also, if you're interested in learning more, we've got the book. If you want to get a discount on that, you can. You can join the AI-powered search community if you'd like to talk about some of these ideas more. And then, of course, Doug and I are doing the live course, which I mentioned. There's a 30% discount throughout this week. And then the last thing I'll say is I've got one physical copy of the AI-powered search book, and I've also got an ebook copy. If you're interested in obtaining one, if you join the AI-powered search community, I'm going to randomly select somebody tonight or tomorrow. So if you're interested, join and you can get a copy. And if anybody joins the class, I'm going to give away one for that as well if you're interested by the end of the conference. So that's it for me. Thank you, everybody. Hopefully that was interesting. Thanks.